The task is to build an autonomous rover that will pick up a wooden block placed somewhere in the maze and bring it to a desired location. The robot's starting location and orientation is unknown, so it has to solve the classical wake-up robot problem. The importance of this problem is that it can be extended to many industry applications where a robot may have to move a payload from one point to another in a safe and consistent manner, such as in Amazon warehouses. We designed our robot with a few criteria in mind. We wanted to minimize our circuit and mechanical complexity without compromising the robot's field of view. Our design solution features a rotating 360-degree LIDAR, which produces 500 beams per revolution. We believe this is a good solution for our localization module because the walls are a relatively invariant aspect of the maze. A lot of our design solution revolves around maximizing the LIDAR's abilities. We mounted the LIDAR upside down and custom machined wheels so that it would be low enough to detect the block without requiring an additional sensor. For our robot framework, we decided to use Robot Operating System, or ROS. ROS provides many mature libraries for localization, path planning, and mapping, as well as a comprehensive set of robot debugging tools. Our gripper mechanism utilizes spring-loaded blades, which converts part of the gripping motion into a lifting motion. This allowed us to use one actuator for the gripper rather than two. The gripper was also designed to be small enough not to obstruct the LIDAR. Our team split the work into mechanical, software, and electrical subsystems, but with a focus on active collaboration. Weekly meetings were set during the planning phase to discuss goals and subsystem updates. Git was used for our software version control process. The metal and acrylic parts were machined in the MC78 machine shop, and the MC402 3D printing facility was used to print the mount for the caster ball. Our team initially planned on using ROS's G-mapping package for map generation. Due to drift in our odometry, there was significant distortion in the map. As a result, we switched over to MATLAB's SLAM map builder, which explicitly looks for loop closures, drastically reducing drift. The initial design of our gripper had a small servo motor mounted on the bottom plate. During milestone 2, we discovered that our servo wasn't powerful enough to lift the 2-inch cube. Then we designed a shaft that extended up through the top plate of the robot, which allowed us to use a larger, more powerful servo while still minimizing the obstruction to the LIDAR's field of view. Our group had a great deal of difficulty synchronizing the clock between the Raspberry Pi and the desktop computer. This time offset meant that we could not visualize ROS messages coming from the Pi properly. We added a time synchronization node to take our faulty time messages from the Raspberry Pi and synchronized them with the host machine. The robot was able to perform the tasks on all 3 milestones without any penalties. Overall, we're very happy with our results, but we feel as though some of the tasks could have been completed quicker. Here are some highlights. Things that worked well for us included the LIDAR localization and obstacle avoidance. Things that could have worked better include the gripper, which was not fully tested from all angles, the driving speed of the robot, which was limited by the PID controller and LIDAR frequency, and also the inability of our local controller to generate smooth trajectories. In this project, we learned how to leverage academic journals for our block detection algorithm. We also learned how to use MATLAB and ROS, and we learned the limitations of many common robotics algorithms, such as the non-optimality of probabilistic roadmap planners, and the poor performance of AMCL when the walls are slightly moved. One thing we might have done differently is having a separate camera for block detection, which would allow us to mount the LIDAR right side up and save a lot of transformations between the LIDAR and robot frames of reference. This would also allow the LIDAR to not be obstructed by pillars, and the camera could also be able to do a visual relocalization.